to the Journey Chez Chem. Well, today I'm so excited because we're doing a lab, and even though we're not going in the lab today, it's a pencil paper lab, what I call a pencil paper lab. It is good practice to see how people had to work with determining where things went on a periodic chart. And we'll use all the information that we've learned in order to complete this lab. Well, you need to please do the 2 warm-up questions to the best of your ability in your composition notebook, and we'll discuss them in a moment. In question number 1, we are discussing a variety of different periodic trends. And you know that you're going to see a question like this on the assessment coming up, and each one of these will be worth 2 points. Just an idea of what's happening. Well, in the first 2, we have atomic size, which is the same as the atomic radius. I use them interchangeably. And we know that for this, we need to take a look at the snowman. Well, the snowman has a little head, and he always falls over in this direction. And when we look at these elements, we see that we are going down the group. And therefore, the smallest would be the sodium. It's very important to read the question carefully and answer what the question is looking for. Sometimes our minds change it and we answer what we think it says rather than what it actually says. That's a very good little tip for study skills. Then we want the largest atomic size, and we notice that we're going across a group. We want the largest, and so therefore that would be aluminum. The least amount of electron affinity. Well, remember, electron affinity is an experimental value that was determined and is measured. And therefore, when I look at this, I see that beryllium is S2 and boron is S2 and P1. And therefore, it is an exception. It's one of the bends. And the least attraction is going to be the beryllium. Then we have the largest electronegativity. Well, electronegativity is a man-made scale, and there are no exceptions. And that's what we're double-checking here, is that we are familiar with which one has no exceptions. And that would be the electronegativity, and therefore the largest will be the boron. Then we have ionization energy, the largest ionization energy. Well, ionization energy also has exceptions because they are measured values. And when we look here, we see that nitrogen is S2P3 and oxygen is S2P4. And you'll recall that nitrogen is S2 like this in my orbital filling diagrams like this, P3. And all of these electrons are spinning the same direction, and therefore it will take more energy to remove the outermost electron versus oxygen, which is S2P4. It's much easier to remove this electron than it is one of these that is spinning, all spinning in the same directions. And therefore, the largest ionization energy here is nitrogen. And you'll notice that I did not give you fluorine, because fluorine would be the greatest in that case. But I wanted to check to see that we understood the exceptions. The highest ionization energy, well, this is just getting used to some different terms. Highest, largest, they're basically the same thing. And again, we have the exceptions going on here because ionization energy is a measured value. And beryllium is S2. And boron is S2P1. And it takes more energy to remove this electron here than it does this lone p electron. And therefore, beryllium is the answer in that case. And that's how you do number 1. Now, hopefully you pulled out your diagonal rule that we've done before in order to do complete electron configurations. Because complete electron configurations have to start at 1s2. And iodine is atomic number 53. So we have to follow the diagonal rule: 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. As we follow the diagonals down, we go to 4s2 and then go back up to the tail to do 3d10, 4p6, 5s2, 4d10, and 5p5. The ending electron configuration is the outermost electrons, and so for iodine, the outermost electrons are the highest energy level. That would be the 5th energy level, and so it would be S2P5, and that would give us 7 dots. And so iodine has 7 dots and an oxidation of -1. Bismuth, that's a big number. Bismuth is 83. So you know you're going to see something like that again. And so we have to follow the diagonal rule. And we know that electrons always go to the lowest level first. And so that's why when we get up into this region, we feel the 4F14 because it has lower energy. And so the outermost electrons would be the S2P3, and that would give us 5 dots and an oxidation number of -3. Selenium, that's a nice lower number of 34, and so we have an S2P4, which gives us 6 dots and a -2 oxidation number. Carbon, we like that number, it's 6. 1s2, 2s2, and 2p2. Not the maximum that it can go is 2p6, but we only need to go 2 because we only need 6 electrons. Atomic number 6, 6 protons, and 6 electrons to begin with. So we have 1s2, 2s2, and 2p2, giving us 6 electrons, 2, 4, and 6. The outer electrons are S2p2, which is a total of 4 electrons around the carbon. And so carbon's oxidation number is +4. And that's just a general trend right now that we're learning, and we'll learn some differences as we go. The next thing I want to talk to you about is how we can do the diagonal rule using the periodic chart. And so that's what we're going to do next. Now that you know how we use the diagonal rule to follow the flow of the electrons to their lowest energy level, I can show you how you can use the periodic chart to do the same thing. And different students prefer one or the other. It doesn't matter as long as you understand that they have to fill the lowest energy level first. So we did iodine in the warm-up. So let's do iodine again. In the periodic chart, we have these first 2 columns that fill the S block, S1 and S2, so there's 2 columns. The D block has 10 columns to fill those 10 possible D electrons. The P block has 6 columns to fill the 6 possible P electrons, S2P1, S2P2, S2P3, S2P4, S2P5, and S2P6. The F block fills 14 electrons. There are 7 F orbitals. Each can only have 2 electrons, so there have to be 7 to get the total possible of 14. We're going to do iodine that you did in the warm-up and follow how it does it in the periodic chart. The first energy level only has a possible of 2 electrons because the first energy level only has an S orbital. So we go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now we know from the diagonal rule that the D block is 1 energy level behind. So we have 3d10 and then 4p6, 5s2, 4d10, and 5p5 for iodine. The next one that I'm going to do is bismuth. Now, bismuth is such a big number that we actually get to the f orbitals. And you'll notice this star here corresponds to this star here. And the reason that we put the f block down below is so that it fits on a normal piece of paper, an 8.5 by 11, instead of a legal size, since we don't use these that often. However, we do need to know that the f fills before this d orbital. And the F is 2 energy levels behind. So when I do bismuth, I go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, and 6p3. So you can use the periodic chart as well. And that works real well. I prefer the diagonal rule, but whatever works for you is fine. You get the right answer. Now we're going to talk about the lab. So your facilitator should give you the lab sheets, and I will give you a little bit of discussion about that. Oh, I'm so excited we're doing this lab. And even though it's just a pencil paper lab, it gets us started in the lab. It counts as a lab. And we get to get some feeling about how those people, those scientists in the olden days had to figure out how to arrange the periodic chart. They had to take all the clues that they knew about all the different elements and put them together and try to come up with some organized way to put the elements on a chart. Well, we're going to use clues to fill in our periodic chart. And I've drawn here the blank periodic chart that you will have. And you only have the first 4 energy levels, and you only have the S block and part of the P block. So this is the very top, and this heavy line here is telling me there's no d orbital elements on here. So this is all that you have to do. And you have to figure out the clues and how to put the elements into these different blocks. Now we're just going to put symbols for the elements. And I'm going to help you figure out how to do this. Well, you're given one of the clues is SW2 is a formula for the gas in carbonated beverages. SW2. Well, I know that the gas in carbonated beverages is carbon dioxide, and therefore my S is my carbon, and therefore I'm going to put the S here. And I know that the W stands for my oxygen, and therefore I will put the W here. Well, I know that the groups of elements, or the symbols for these elements, is given in groups, and therefore they are going down. And I look for the group that has the S in it, and it would be the ZFS. And I know that I have to figure out which one, does the F go here or does the F go here? Well, I have to figure that out based on the clues that I'm given. And then I know that the WHN are the groups that are together, so I like to write it down below, and then I have to figure out, does the N go here or here based on my clues. It's a fun assignment. I know you'll like it. And it counts as a lab, so that's a good thing. Well, please do the best you can, and I can't wait to see you tomorrow. Bye.